So this is my lab report for Physics 2212 Lab 6 called Magnetic Braking with Faraday. To introduce this lab, the purpose of this lab was that we wanted to analyze and find the magnetic induction of a bar magnet with its north facing up as it falls through an aluminum tube. So there is a magnetic force there, and compare it to a computational model using GlowScript or Python. Um, some basic physics principles here. To start with, we have Faraday's law, which states that the EMF is equal to the negative change in magnetic flux over time. And then secondly, what we've been working with, basically all this unit, is the Biot-Savart law. Right here I have it in dB and dL instead of B and QV, but still the same thing. This is just more important for computational model. To preview our results, so the average time for our experiment for the magnet to drop through the foil was 1.118 seconds, and the time predicted by GlowScript was 1.491 seconds. So to describe our process that we did in lab, first we took the measurements of the aluminum. So this little tube of foil right here, we got its length, the width of the foil right here, so we're the inner foil and the outer foil, what's in between there, and then the inner radius also. We found the magnetic north of the magnet and then wanted to drop it with that magnetic north oriented upwards through the foil. And then we repeat that 5 times. Multiple trials means 5. And we record a video each time to see what the time looked like. So this is what the time looked like in each of our videos. It came out to an average time, like I said, of 1.118 seconds. And here were our dimensions. So I already told you about the tube dimensions. We also have the magnet dimensions, which are from the previous lab. So we had the magnet 0.023 kilograms, and that dipole moment we calculated in lab 4 was 3.79. Next, here's our code, or my code. So right here, I have the initial conditions listed. I have my constants, I have the dimensions for the magnet, and I have the dimensions for the aluminum. And I don't have all of the functions here. You can check out all of my functions on the GlowScript code, but here I have 2 of the most important functions. We have the one that describes to find the magnetic force, dipole magnetic force. And this one uses the off-axis formula, which is good in cases where we can't approximate using the on-axis formula. And then right here, I have the change in flux function right here. And then here's what the code would output. So right here, I have my 2 visuals as the red is the south and the blue is north. It kind of just fell. That's what it looked like in the middle. It's what it looked like at the bottom. And then here is my graph of velocity versus time. Again, we got that it took to drop 1.491 seconds. So some comparison between our model, or my model, and our experiment. So general statement is that the computational model probably predicts a stronger force between the aluminum and magnet because the time it took to fall was a bit longer. And some reasons for this might be that we could have incorrectly measured the aluminum foil. And then we might have had other forces on the magnet in that experiment. We might have pushed down with our hand. There might have been more or less air resistance in the tube than we anticipated, stuff like that. And then lastly, some wrap-up discussion questions to start. What if the resistivity of the conductor were reduced as close as possible to 0? What this means is that the current in that equation, EMF equals RI, that current would have to be much stronger if the resistance went down. And with a stronger current, that also means that your induced B field would be stronger, which means there would be more of a force on the magnet, and it would take it'd take more time to drop. Sorry. And then lastly, what if there were holes cut all over the tube? What this would do is, the way that this force comes about is that there's cross sections of current in little rings around the aluminum foil. And if you cut holes, there's not going to be as many of these cross sections, and therefore there's not going to be as strong of a B field, and therefore the force on the magnet isn't going to be as great, and it'll drop a lot quicker. Thank you.